Let us see the fifth experiment of wireless and mobile communication. Okay, that is nothing but simulation of OFDM transmitter and receiver using MATLAB. Okay, so all the specification that is required for us to design this system will be given to you, and accordingly we will have to write the MATLAB code. Okay, all right. So what is basically this OFDM? Okay, so you would have already studied about this. So if I have to properly define it, I would say that this OFDM, that is nothing but orthogonal frequency division multiplexing. It is a method of digital signal modulation, okay, in which you will have the single data stream which is split across several separate narrowband channels, okay, which we call it as subchannels or subcarriers at different frequencies, and we do this in order to reduce the interference or crosstalk. Okay, so this is an advanced FDM, I must say, okay, frequency division multiplexing scheme, okay, wherein the closely spaced orthogonal subcarrier signals that you will have, okay, with the overlapping spectrum are transmitted to carry the data in parallel. Okay, so we will be sending the data in basically parallel using the different subchannels or subcarriers. Getting my point? So that is a basic point of our OFDM. So a stream of data basically, okay, serial stream that has to be converted to parallel stream, okay, which is propagated using your, different subchannels basically. Okay, so now if I have to differentiate this, okay, with respect to your conventional FDM, okay, you can see the signals, okay, or the subchannels, individual subchannels, okay, that we have, they are not orthogonal to each other. In order to separate it, okay, in order to separate it and to avoid the interference, okay, we would require the guard bands. Okay, that is what you see here. This is in case of your FDM. Okay, so this is what we can represent as your OFDM. Okay, you can see all the signals that are there. Okay, the subchannels, okay, they are orthogonal to each other and there is no interference basically. Okay, so now if I have to talk about inter-symbol interference, okay, one problem could be if our signal is propagating without any time delay, okay, or without any propagation delay for that matter, okay, there will not be any interference. But in case if there is any delay in the symbol transmission, you can very clearly see here, which is denoted as this in blue color mark. Okay, see, if the signal, the red color line, okay, if it is delayed by any chance, that it may happen that that part of the signal may get actually lost, because that may get interfered to the subsequent symbols that is getting transmitted. Getting my point? So in order to avoid this, the one solution is nothing but you can go for using the guard band. Okay, provide sufficient spacing. Okay, but the hardware basically does not allow this. Okay, and one of the best method to solve this part is, see, you can see the tail part of the symbol is basically getting lost, because basically it is getting merged with the subsequent symbols that is getting propagated. So what actually we do is we come up with a technique called as cyclic prefix. Okay, cyclic prefix, basically what happens in this cyclic prefix is the tail part of the symbol, okay, the tail part of the symbol is copied and it is pasted to the front portion of the symbol. Okay, so in case if this tail part of the signal is getting interfered with the subsequent symbols which is getting propagated, okay, even if there is any interference that is happening because of the delay of this particular symbol, okay, we don't end up losing the data because we have already copied and kept it at the front part. So the same concept we will be making use in the coding in MATLAB. Okay, so cyclic prefix, it is very, very essential. Okay, so prefix, in the sense, the name prefixes there. Why? Because we are adding this to the front. Okay, adding the tail part of this symbol to the front of it. Okay, so that prefix name is cyclic. Cyclic is because we perform a circular convolution basically. Okay, a circular convolution will be performed basically. So this is cyclic prefix. Okay, all right. So now this is how the signal basically, OFDM transmission reception, it is both showing. Okay, in terms of its waveforms, you can see this is our the data is getting propagated, which is in the frequency domain. We take the inverse fast Fourier transform to obtain the separate signals in the time domain. The signal gets transmitted. Again, at the receiver, you have the signal received in the time domain, which further converted into frequency domain, and that can be decoded separately. Okay, so coming to the block diagram, okay, of the OFDM and transmitter as well as the receiver. So if we have the signal here, that will be modulated. Okay, the signal will be modulated, and the serial data, the data that we will have at this point of time, will be the serial data that will be converted into the parallel streams. Okay, parallel streams, okay, which will be in frequency domain, and taking the inverse fast Fourier transform of it, we would convert that signal to its corresponding time domain. Okay, now we would the insert the cyclic prefix. I told you the reason why we need this cyclic prefix. So in case, we never know, in case if there is any delay of the symbol transmission, in order to avoid the interference with the subsequent symbols that is getting transmitted, we go for inserting this cyclic prefix. Okay, then this parallel stream of data is converted into the serial stream and given to an digital to analog converter for the transmission. So while it is getting transmitted, it may get added with the noise. Okay, then it comes to the receiver part, exact reverse process of what has happened in the transmitter side. That is, whatever you signal that you have obtained, we are converting that signal to the digital. Okay, then the signal that you have obtained is nothing but the serial signal that is converted into parallel. Cyclic prefix that you have added, that has to be removed, converted back into your frequency domain, and then again the parallel stream of data is converted into serial, and demodulation has been done on the signal that is obtained to, in order to get the actual signal. Okay, so now the entire thing that you are seeing here, okay, has to be implemented using the programming, okay, in MATLAB. Okay, that is what we are going to see here. Okay, now let us move to the coding part of it. Okay, so you can see I have my code written at the left hand side, as well as the corresponding output, which would make you to understand this program much easily. Okay, so all that the first thing that we have is nothing but the initiation part. Okay, so all the specification that I have given until this block size will be given in your aim. So accordingly, you may have to modify the code that you will basically write and give. Okay, so the number of bits that is given is nothing but 64. Okay, and the m value, we are assigning a value m will be nothing but the number of subcarrier channel that we would be making use. In our case, it is 4. Okay, and number of bits is 64, and the small n is given a value 256. That is nothing but the total number of bits to be transmitted at the transmitter. What is this block size? Block size is actually given as 16. Okay, that is nothing but 64 divided by 4, that is 16. Okay, now we have a variable that is being assigned here, that is nothing but CP length, and it is equal to what? It is equal to floor 0.1 into block size. So what is our block size? 16. So 0.1 into 16, it will be equivalent to 1.6. Okay, so since it is a function floor, so it would consider the CP length value as 1. Okay, and that becomes the length of our cyclic prefix. Okay, so I've already explained what is the cyclic prefix, so you must be knowing it. Okay, all right. So now when it comes to the transmitter, you can see, okay, transmitter, what are we doing basically? The first thing that we are doing is we are generating a matrix. So that is being assigned the value data. Okay, it is generating a random data first. Okay, I must say it is generating the random data first. And what is happening here? How is it generating? You can see this random source one row with number of data bits. Okay, number of data bits. Okay, as number of data bits for our case is nothing but 64. Okay, so 1 comma 64. Okay, so if you consider the serial data, okay, so how it will be, you consider this to be as one row and 64 columns of the range, the value it takes from 0 to m minus 1. So what is our m value? M value is 4. Okay, so 4 minus 1, 3. So it will take the value correspondingly from 0 to 3. So if I can probably show you the uh, graph here. Okay, so you can see here, the values from 0 to 64. Okay, and the range it is taking is from 0 to 3. You can very clearly see this, right? Okay, so this is done. So we are just plotting it. That is what I have shown you the plot. When you run the code, you will plot it. So we are going step by step in the block diagram. So what was the second thing? The first thing, or majorly the first thing, we have considered the data, right? Okay, now we are performing the modulation on it. We are performing a PSK modulation. So we have an inbuilt function for it, okay, in MATLAB. So PSK mod data comma m. So already we have all the datas here, right? So what it would mean, what it would do, this would modulate the input signals that you have, okay, the input signal data that you have with the modulation order that you are specifying here, that is nothing but 4. Okay, so you would again have the graph plotted for this, and that would look like, you can see here, the modulated PSK modulated output, which will give you a complex value. Okay, that is what you see at both positive and negative side of it. Okay, all right. Okay, now next thing what are we doing here is nothing but we are making an attempt to convert this data, okay, the serial data into the parallel, okay, parallel stream. Okay, how are we doing? We are making use of an inbuilt function as reshape. Okay, and the input that we are taking is nothing but from the PSK modulator. Say we had the data which we have modulated. Now we are going to work with the modulated data, and we are going to put that into a matrix called as your S2P. Okay, S2P. And what about the number of rows and columns? That would be decided by, you see, number of data bits divided by m. So what is the number of data bits here? 64 divided by m is 4. So 64 divided by 4 is equal to 16. 16 comma 4. So you would ideally obtain a matrix, okay, which will have all the modulated data arranged in 16 rows and 4 columns. That is what you will have in your S2P. So if I have to show you this here, you can very clearly see this. Okay. Just scoop it up and I'll just show you this. Okay, the corresponding value. Much easier for you to understand it would be. You can see this. Okay, so you have the corresponding values. 1, 2, 3. Okay, your S2P that you would basically obtain, okay, will have, you can see 1, 2, 3, column 4. You can see the space is not there, so it has come down. Okay, the space is less, so it has come down. Okay, you can see here column 1 to 1 through 3. You can very clearly see this. So what was I basically doing here? So S2P reshape. So I have taken all the data. Okay, so number of 16, number of rows are nothing but 16, and number of columns are nothing but 4. So you can see 1, 2, 3. You will, if you count down, this is nothing but 16 rows, and how many columns? 4. 1, 2, 3, and basically 4. Okay, and where are you saving this and keeping? You're saving and keeping this in your S2P. Is that okay? Now, what are we doing? We are having 4 different sub channels. okay, or subcarriers. So we are picking up the data from this S2P and separately we are writing it. How all the elements of your first column, all the element of your second column, third column, fourth column, separately we are placing it in subcarrier 1, subcarrier 2, subcarrier 3. You can very clearly see here. You have your subcarrier 1 here, you have your subcarrier 2 here, subcarrier 3 and subcarrier 4. This is nothing but as it is the data that was there in S2P, we have taken and kept it separately because we are going to perform the inverse fast Fourier transform on it, which would convert the frequency domain signal into the corresponding time domain. Okay, so this is again plotted. Okay, this is again plotted. You can very clearly see the different depending upon the values, subcarrier 1, 2, 3 and 4 here. Okay, all right. Now next thing what we do is here is nothing but we are trying to perform the IIFT. That is, I told you the reason why we take it. Now for that, before that, what do we have? Number of subcarriers is 4. We have a parameter called as substart, and what is the value of the substart? This is equal to block size minus CP length. What is a block size? A block size is 16. CP length, we have evaluated that as 1. So what will be there in CP start? So you will have the value CP start equals to 15. Okay, remember this and keep. We would be making use of it. Okay, now individually we are performing the IIFT on every subcarrier, and that is again held in another matrix which is named as IIFT subcarrier 1, 2, 3, 4 correspondingly, and that is what you see here. Okay, and that is what you see here. You have taken the inverse fast Fourier transform on individual subcarrier. Okay, and that is what is you're seeing here. Can you see subcarrier 1, again subcarrier 2, and you have your 3, and you have correspondingly the fourth one. Okay, now we are trying to combine this, okay, this IIFT subcarrier matrix, a single matrix, with the help of, okay, before doing that, we would work on our cyclic prefix, which is the major part. I told you step by step we are going IIFT, now the cyclic prefix. Okay, so this is again whatever IIFT subcarrier 1, 2, 3, 4 you have obtained. Okay, that is again plotted. Okay, so you have 4 different, which was in the frequency domain, has been correspondingly converted into time, and this also you can see once you run this in your MATLAB. Okay, all right. Now let us see this cycling prefix part. So for I equal to 1 to number of subcarriers, okay, so we have I ranging from value 1 to 4 as a number of subcarrier is 4. Okay, IIFT subcarrier, this part you see, I will come to this and then we'll go back to this. Okay, so you are performing IIFT on, you are performing at 16 point, that is what is it is mentioned here, 16 point inverse fast Fourier transform on, okay, different columns that you have, all the elements of different column depending on the value of I in the S2P matrix, and you are saving that in a matrix, okay, all together. So IIFT in first instance, it will take the value of IS1, then second column, then third, then fourth. Okay, so all this IIFT taken value, that is 16 point inverse fast Fourier transform performed values on the different columns of S2P, which is comprising of all the elements, will be now available slowly in IIFT subcarrier 1. How? With the help of the prefix value also. That is, we would be adding our prefix also simultaneously. Let us see how we are doing that. So if you assume now the first column of S2P, you have performed IIFT, you have the value. Okay, now you have stored and kept that value in IIFT subcarrier, the first column. Okay, that is what you have here. That is what you have here. This is what you're seeing this. Okay. Now for j equal to 1 to CP length, our CP length is nothing but 1. Okay. So our j value 1 to 1, that is nothing but you can consider 1. Cyclic prefix j comma I. Okay. So 1 comma 1 for the first instance when I is 1. Cyclic prefix 1 comma 1. Okay. What do you have? What do you have? In the IIFT subcarrier matrix, okay, j plus CP start. J is 1, CP start is 15. So 16th row first element, the 16th row, the first element, okay, that is nothing but this, okay, that you're seeing is taken and put where is taken and put in separately, that is cyclic prefix 1 comma 1. That is what you are seeing here. Same element you have here, right? Now next, what am I supposed to do? I'm supposed to end the I'm supposed to append the prefix. Okay, how will I append the prefix? Append the prefix to what? To the, you can see append prefix. Again, I'm having another matrix wherein I'm performing some concatenation. What concatenation? Now I have the IIFT subcarrier, right? I have, look at the right hand side here. I have the IIFT subcarrier here. Okay, I have the cyclic prefix as well. Okay, so now how am I going to concatenate? I'm going to concatenate this cyclic prefix with this IIFT subcarrier. So I would go for making use of a MATLAB function that is called as vertical concatenation. When I do that, all that I will get is nothing but this particular value will be concatenated. That is, this will be put as the first element. Okay, this would be put as the first element, and this would be combined with the rest of the IIFT subcarrier values. Getting my point? So if you see this append matrix, now here it was 16 element. Last value is taken and put in the first as the first element. So it was 16. Now it should become 17. So now if you see this append prefix matrix, you will have 17 element. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. And the last and the first element, if you see, they both are same. Why? Because we have copied the tail of it and glued it into the front. Getting my point? Similarly, what you would do, you would do for, you have done for I equal to 1. So you would do this for I equal to 2, I equal to 3, I equal to 4. So all the IIFT subcarrier last values, you would take and put it in the cyclic prefix as such. Okay, you can see. Okay, you have taken the next row element, cyclic prefix you have, then again perform the append. Okay, similarly take the IIFT, the third one. Okay, the third one you take, you will have your cyclic prefix also. Okay, the third last element of this you can see here, the last element. Okay, and put that in the append matrix. Similarly, you will have your last matrix as well. Okay, so 4 you have, right? 4 you have. So you will take and put that, the fourth column, take this last element. It will come to the cyclic prefix. Okay, where is it? It is here. Okay, it is, let me just come here. It is here. Okay, so what would you do? In append matrix, you will have the last column also appended. Is that okay? So the now number of rows that so you have vertically concatenated, you have taken the last element of your matrix and you have glued it to the front. That is nothing but basically it is literally trying to say that you have taken the last part of your signal, okay, or the symbol, and you have pasted in the front, so that in case if there is any interference also taking place, if we lose the end part of the tail of the symbol, okay, due to interference, we can easily retrieve that back because we already know that is there at the front part. Okay, so what is happening? So we had 64 elements when we had started with, right? That was the length of our data string, okay, or bit stream. Okay, now 4 elements. Okay, now it's the copy. Okay, so extra, right? So now 68 element will be totally available. Is that okay? So the cyclic part, it is added. That is what that append prefix one I have showed you. Okay, you can again see in the graphs. This is nothing but cyclic prefix is added. Okay, you can see the cyclic prefix will be added. The tail part of it is copied to the front. Okay, you can see tail part is copied to the front. Okay, and then this particular graph is just showing the orthogonality. Okay, so we are plotting the orthogonality also. You can see different colors. So these symbols are orthogonal to each other. That is what is being indicated here. Okay, then now what are we doing? We have to further convert this into the serial stream for transmission. Now we have as 17 cross 4 with 17 rows. So if you see this last matrix of append prefix, now you will have 17 elements with with 4 columns, right? Now we have to convert that into single serial stream. So we are making use of a function called size, okay, size of the append prefix, and the length of that is taken as number of rows. And so the size would give you the number of rows and number of columns. Okay, this MATLAB function would give you the number of rows and number of columns. Okay, so once when you take that, you know number of row and column. When you multiply that, you will get the number of total elements. So in our case, it will be 17 cross 4. So length of the OFDM data will be 68. I told you how it got converted from 64 to 68. Okay, now in order to convert the stream of data which is in parallel to serial, again we are making use of reshape signal, append prefix, take all the value from the append prefix. How are you arranging it? One row and these many columns. What is the length of data here? It is nothing but, in our case, it is 68. So one row and 68 column. You can visualize it. Okay, you can very easily visualize it, and you have the stream of data ready to be transmitted. Okay, so even for that, I have the plot here. Okay, you can see here. Okay, the data moving up to, you can see here, the data is moving somewhere up to close to this particular point, which we can assume it to be 68. Okay, so 68 bit streams. Okay, so the length of the stream now, it has increased, number of bits have increased by 4 here because of the cyclic prefix. Okay, all right. Now when it comes to the reception part, okay, when it comes to the reception part, it is actually the same. Okay, it is actually almost the same, exact reverse. Procedure remains the same, exact reverse of that. So when we receive the signal, okay, whatever signal that we have received, okay, that is in serial, that we would make use of reshape function, and we would convert that into parallel stream. Okay, and whatever prefix that we have added, cyclic prefix, that has to be again removed. That is what you have done. You have separately placed in R1, R2, R3, R4. Okay, the matrix that we have removed. So here we will get back the 64 bits itself. Okay, so again we have written a for loop, okay, in order to perform the FFT, like how we perform by FT. Now here the time domain signal that you have again has to be converted into frequency domain, same as the block diagram. Okay, all the steps, and further the signal is reconstructed, that is, you have converted the stream into serial. Okay, and then you are demodulating to obtain your final signal. So you can very easily simulate it. The transmitter part I have shown with the code. Receiver part also you can analyze. It is exactly the opposite of it.